Hello, folks. I hope things are going well for you. This is Mike coming back at you here with another video on discrete mathematics. In the previous video, we looked at some sample problems where we used truth tables to determine whether or not two logical forms were logical equivalents of each other or not. In this video, we're going to continue on with more logical operators that we have. We talked about the not, the and the or operators, also known as the negation, conjunction, and the disjunction. Well, in this video, we're going to talk about the conditional, conditional statement, the conditional operator as well. So if we have two portions of a sentence, or two statements, one represented by P and one represented by Q, then the conditional is written as if P, then Q. It can also be stated as P implies Q. And symbolically, we denote this by P and then a right-facing arrow, and then Q. So P implies Q, P arrow pointing to Q. And the truth table for the conditional is as follows. You have P and Q and all possible combinations of truth values, and then you have your conditional P implies Q. A true implying a true means that the conditional is true. A true implying a false is a false. A false implying a true is a true. And then a false implying a false is actually true. So in most cases, your conditional is true, except for only one case, when you have a true implying a false. In the conditional, in the if P then Q, that first batch of stuff that follows the if, so the P, we call that the hypothesis or hypotheses, and Q we call the conclusion. Now, I want to just make a quick note about the last two rows of our truth table here. Notice that the hypotheses are false, and the conditional is always true. There's a special term for that. We say that the conditional statement in that case is vacuously true. So sometimes a conditional statement is true because the hypothesis or hypotheses are false. If this is the case, then we say that the conditional statement is vacuously true. So as a quick case in point here, the statement or the sentence, if a pig can fly, then it is green, is actually vacuously true because the hypothesis is false. At least last time I checked, pigs cannot fly, so therefore it is logically valid to make this conditional statement. If a pig can fly, then it is green. We can't infer anything about the conclusion of our conditional statement or conditional sentence, so therefore we have to go with the fact that it is true. In a similar way, just one more sample, if I have traveled to Mexico, then I own a sombrero. Well, if I have not traveled to Mexico, which I personally have not, then that is a vacuously true sentence. It's a vacuously true statement because the hypotheses are false. So, up until now, we had three logical operators, the not, the or, and the and now we have the conditional. We have the right facing, or the rightward pointing arrow. We have the conditional being thrown into our list of operators as well. Where does this fit into the order of operations of our logical operators, for lack of a nicer and shorter phrase? The negation still takes place first. If we have nots, you're going to do those first. Then next are your conjunctions and or your disjunctions. And then third, the conditional is done last. And in the next video, we're going to see some samples where we construct truth tables for logical forms involving nots, ors, ands, as well as conditionals. But that's coming very shortly. Does a conditional statement have a logical equivalent that does not involve an implication? Is there some logical equivalent to P implies Q that does not involve a rightward pointing arrow? It does. And the logical equivalent of it, as you can see here at the very bottom, is not P or Q. In our next video, we will construct the truth tables for these two logical forms, and we'll see that these things are indeed logically equivalent. They have the same truth values no matter the combination of truth values for P and Q on their own. And this form all on its own, this not P or Q, we don't typically use that in everyday talk. Just as a quick case in point here, if I take the statement, if it is 100 degrees outside, then I will be inside. So if I break that up into a conditional, if it is 100 degrees outside, then I will be inside. The logical equivalent of that is it is not 100 degrees outside, or I am inside. And that's something I may have misstated just prior to this. The logical equivalent is not P or Q, not P and Q. That is my bad. So logical equivalent of P implies Q, not P or Q. Yeah, so we don't typically say it is not 100 degrees out or I am inside. We say if it is 100 degrees out, then I am inside. So how do we take the negation of a conditional statement? Well, now that we know a logical equivalent, we can easily come up with what is the negation of a conditional statement. What is the negation of P implies Q? We do it with De Morgan's laws, as we saw from one of our previous videos. So not P implies Q is logically equivalent to not P or Q. And remember, De Morgan's laws said that you apply the not to each term or each thing inside of your parentheses. And then you also switch the sign. The disjunction becomes a conjunction, or the conjunction becomes the disjunction. So when you do that, you get P and not Q. So the negation of not P implies Q is P and not Q. Those are logical equivalents of each other. And later on in this course, we'll see that this is somewhat commonly used when proving mathematical facts or mathematical theorems. If you're given a conditional statement and you have to prove it, sometimes you begin by assuming the negation of what you want to prove and show that it leads to some problem. And thus you know that the statement that you are given has to be true. So this is just a little bit of an overview of the conditional statement, the conditional logical operator. The truth values of it is logical equivalence, and where does this fit in the order of operations for these logical operators? As I said, in the next video, we are going to be doing some truth tables with the conditional operators, seeing how these things work. And then we'll also show a couple cases of things involving conditionals either being logically equivalent or not being logically equivalent. If you have any questions or comments, be sure to drop them in the comments section below. Otherwise, until the next video, take it easy, guys.